Okay, we're starting. So remember on Wednesday we have our first test. Test 1, Wednesday, 9/28. I don't remember if I told you guys, but it's 5 problems long. 1 hour, 15 minutes. Of course, they have the marks. It's algebra. So, things like simplifying. So fractions, rational functions, all sorts of stuff. Including simplifying exponentials and logs. And log expressions. But of course all the other kinds of simplifying as well, so fractions and things like that. Graphing, of course. So some basic graphs, just like the ones I actually quizzed from previous quizzes. What else did I ask you? I said about lines, finding an equation of lines. Solving exponential and log equations. What else did I using algebra to solve word problems. So remember that, like that hot dog stand problem that we had in lecture 2. For example, so there's composite functions, domains. Yeah, so it's an algebra-based test. Of course, I have bonuses on it. So, which would maybe be like limits, maybe derivatives, because right after we finish limits, which we will do today, we will talk about derivatives. Yeah, I think that's it. I don't remember what order I put these in, but I think that covers everything. So that's on Wednesday, so hopefully you're prepared for that. As for the remainder, let's continue with limits, which I think we were doing in 2.2. 2.2. Which we were talking about continuity. Just recall the definition. I did give you the definition. So f of x is said to be continuous at x equals a if the limit as x approaches a of f of x is equal to f of a. It's a very important definition. This is a very important equation. So you should know that equation. That's what makes something continuous. The limit as you approach a point actually equals to the value of the function. The function is continuous there. What this means for the picture is I'd be able to draw through the point, that region of the graph, without lifting my pencil off the page. A very important property, which we will get to why it's important. So this is talking about continuous at a certain point, and then we just say f is continuous, like in general, if it is continuous at all points on this domain. let's actually practice this. So limits are pretty useful. They define continuity, the idea that your graph keeps going and you don't have to break it. And they will be defining both derivatives and integrals, which are the two stars of calculus. So let's actually look at some examples here. I think this. I gave you this definition in last class, so it's just a review. One big example. So we're going to try to figure out how to figure out something is continuous or not. I don't know, turn your big landscape or something. I'm drawing a huge picture. Gonna get a lot of practice out of this one problem. So let's say my function is coming from all the way up there. Piecewise function. Here, here. Do this. Put some numbers here. Let's see, all these guys are at level 1. This guy here is at level 2. This guy here at level 3. This is at level 4. Let's make the x value for this minus 10. 8, minus 7, minus 6, minus 5, minus 4, minus 3, minus 1, 0, 2, let's say this is 5, let's say this is 8, let's say it's 11, let's say it passes through here, 12, so here's the question. I'm going to ask you to determine where this function is continuous at all these very specific points. Now, intuitively, just by looking at the picture, this is shaded, we can sort of see what the answer should be. Would it be continuous here? No, because I have to lift my pencil out of the page to fill that gap. Would it be continuous here along minus 8?
Yeah. Positive and negative?
Is it continuous through minus 8? When x is minus 8, is the function continuous? No, because I can't draw through minus 8. I have to go here, lift my pencil up, and start drawing from there. Is it continuous at 7, minus 7? No, because there's a gap that I have to jump over. What about minus 6? The answer is actually no, because I can't connect the left side. Right? About 5? No. 4? What about at 3? Sure, if I zoom into 3, I'd be able to draw without lifting my pencil off the page, that section. So we expect that to be continuous. What about here? No, because I'd have to lift my pencil up to jump over that gap here. No, because I have to jump down this gap. What about at 5? No, there's no graph there. I can't even draw it there. 8? Yeah, I can draw right through at 8? 11. No, I'd have to jump over that gap. 12. Yes, okay. So by looking at the picture, it's easy to tell, but there are cases, of course, where we don't have the picture or we don't want to draw the picture. The function is very complicated, and we need to be able to tell when something like a curve behaving like it's behaving at 8 happens, and when something like this happens, or that happens, without actually drawing it. Right? Because a lot of times we won't be able to draw it. So we want to be able to do this with computations. And basically what we're going to do is we're going to do the definition. So let's actually see why it's not continuous at x equals minus 10. So let's do x equals minus 10, and we're going to examine the function here. Okay? So remember, continuity means the limit is equal to the y value. Right? So let's actually find the limit. What is the limit as x approaches minus 10 from the left of our function? Say 2. Why do you think the answer is 2? Why do you think the answer is 2? What is the limit?
The y value.
The y value that you're approaching as x is approaching something, right? So you look as you're approaching 10 from the left side, and look, what is that y value?
2.
So you trace it over, it's 2. What about the limit as x approaches 10, minus 10 from the right? So I'm approaching minus 10 from the right side. What is the y value? It's again 2. So our limit exists here, right? So that's fine. So I know that the limit is equal to 2. What about the value of the function? What is f at minus 10? It's undefined, right? So notice that the limit exists, it's 2. But the function itself is undefined, which means that equation doesn't work. So it means it's not continuous here. Not continuous, right? Because the limit exists, but the function doesn't. So there's no way they can be equal. What about at minus 8? So if I go to x equals minus 8, what's happening here? What's the limit? Remember all the space here. What is the limit as x approaches minus 8
0.
from the left, our function?
Negative infinity.
Negative infinity. What about the limit as x approaches minus 8 from the right of our function?
Positive.
It's positive infinity. As I'm coming from the left, what's happening to my y values? They're decreasing without bound. It's going to negative infinity. Coming from the right, they're increasing without bound. That's positive infinity. So the limit does not exist here. And so it's not continuous. Does f of minus 8 exist? That's also undefined. So here, everything messes up. Both the limit and the function messes up. There's no way they can be continuous because you can't put them in an equation. What's happening at x approaches minus 7 from the left, x approaches minus 7 from the right. What's the limit as x approaches minus 7 from the left? It's 1. X approaches minus 7 from the right. It does not exist. Right? There is nothing on the right. I can't get close to 7 from the right side. There's nothing there. So limit does not exist. So limit messes up. What about f of minus 7? What is that? There's a hole, so it's also undefined. So I know it's not continuous here. So that's an NC, that's an NC as well. So it's not continuous at those 2 points. What about minus 6? So we're going to check limit as x approaches minus 6 from the left. Limit as x approaches minus 6 from the right. And try the function evaluated at minus 6. So what's going to happen for minus 6? Approaching minus 6 from the left, what's the limit?
1. Undefined.
Undefined, does not exist. There is no graph to the left of minus 6. There's a whole gap. What about from the approaching minus 6 from the right side?
1.
It's 1. So limit does not exist. So I already know that it's not continuous there because the limit doesn't even work, but for fun, the remaining, what's f of minus 6?
1.
It's 1. It's actually filled in, so it can have a value. So that's 1, but it's still not continuous there because the limit doesn't equal the value of the function. Okay. How do we examine minus 5? Tell me what I need to check. Limit from the left and right. So x approaches minus 5 from the left. X approaches minus 5 from the right of the function. And I need to check what is f evaluated at minus 5. Now in order for this thing to be continuous, all of these have to give me the same value. That's the idea. So what about minus 5? Limit from the left. Limit from the right. F of minus 5. Right? Not continuous. Where I check for minus 4.
Limit as x approaches minus 4.
What's this?
Undefined.
Does not exist. This?
Or
This?
undefined.
Not continuous. Hopefully we're getting the idea. Let's start from over here. What's the next important number? -3. What's going on at -3? What do I do? Limit. So limit as x approaches minus 3 from the left. Limit as x approaches minus 3 from the right. And f evaluated at minus 3. So limit as I approach 3 from the left side. 1. So limit as I approach 3 from the right side. It's also 1. So I know that the limit is equal to 1. Okay? What is the value of this? It's also 1. So look, they both match up. It means that this guy is continuous. Right? So these three numbers all match up. It means that I can draw right through minus 3 without lifting my pencil off the page. Because all of these guys match up. Right? Both the left and right hand limits connect, and the function is actually filled in at that point. Do the same thing for minus 1 from the left. Minus 1 from the right. F of minus 1. Okay, what's going on here?
4.
4. 4. So the limit actually exists, and it's equal to 4. What about the value of the function?
Doesn't exist.
Undefined, which means not continuous. I have to lift my pencil off the page here in order to draw through that. Let's keep going. Where are we? 2. What's going on at 2? Limit as x approaches 2 from the left. Limit as x approaches 2 from the right. And f of 2. What's limit as x approaches 2 from the left?
Does not exist.
Huh?
Does not exist.
It exists. It's 4. What about from the right? 3. So limit does not exist. What about at 2? It's 3, right? It's filled in at 3. There's a gap at 4. So at 2, this is the value that it takes on. Let's continue. Limit as x approaches 5 from the left. Limit as x approaches 5 from the right. F of 5. Negative infinity. What about this one?
Negative infinity.
Awesome. Which means that the limit is equal to negative infinity. What about the value at 5? Undefined. So obviously it's not continuous here either. Here it's not continuous either, because the limit didn't exist. What about at 8? Limit as x approaches 8 from the left, our function. Limit as x approaches 8 from the right of our function. And f of our function.
2. 3 or 2?
Well, it's a little, I didn't. That would be 2 from the right. Same thing, 2. So the limit equals 2. That's evaluated at 8. Also 2. So it is continuous here. Between 8, I can draw right through the point 8 without lifting my pencil off the page. This is how I would know I could do that. Let's look at what's going on at 11. 11 from the left. 11 from the right. And f evaluated at 11. Limit exists and it's the value is 2. What about the value of the function?
Undefined.
It's undefined, which means not continuous. Let's do the 12. 12 from the left. 12 from the right. F of 12. Limit as you approach 12 from the left side.
Negative infinity.
0. Well, from the right side. It's also a 0. So limit exists and it's equal to 0. What's the value of the function at 12? It's also 0. It crosses the x-axis at 12, so that's why it's 12. So these all match up. They're all 0. So right here, it's continuous. Because I can draw without lifting my pencil off the page. And when these 3 things happen, that's exactly when a graph will behave that way. Okay. Then I need to erase. Finish copy. Are we okay? Can you get rid of it? So the moral of the story. We learned about continuity. It just means that that equation makes sense. And basically that equation making sense just means testing 3 things. So let's just actually summarize this. It asked whether a function f of x is continuous at x equals a. You're going to do 3 things. 1, you're going to find the limit as x approaches a from the left side of f of x. 2, find the limit as x approaches a from the right of f of x. 3, find f evaluated at a. And then you're going to have point 4. If all the above give yes, f is continuous at x equals a. Otherwise, it is not continuous. Which is basically the idea. So continuity just comes down to checking that a limit exists and checking that the function is defined at the point, and all of these have to coincide, right? So when asked if a function is continuous, which odds are on test 2, I'm going to ask you something like that. These are the 3 steps you're going to go through. So you need to know how to do limits, right? It'll depend on the function. You might not have the graph. I can give you a formula and say, test this function whether it's continuous at this point. And those are the same 3 steps that you would go through. So I can ask you some examples. So let's get some examples of that. I can ask you here, is the function continuous at the indicated point? Start with something nice, like f of x equals x squared at x equals 1. Or b f of x equals x squared minus 4 over x plus 2. Let's do a variation on that. F of x equals x squared minus 4 over, at the point x equals minus 2. X is not equal to minus 2. And let's give the value minus 4 if x equals minus 2. So instead of a piecewise function. One other variation. So you don't have to be given a picture, you might be given a formula. So let's just illustrate the idea here. So x, is the function continuous at this point, right? So I want to look at y equals x squared at x equals 1. Is it continuous here? So what will we check? Limit as x approaches 1 from the left of x squared. What would the answer be? 1. Limit as x approaches 1 from the right of x squared. 1. And what is f of 1? You plug in 1 here, you get 1. So, what's the answer? Yes, it is. Right? What about here? At x equals minus 2. And all of these are at x equals minus 2. Limit as x equals approaches minus 2 from the left of our function. What would I get? What do I get?
Minus 2. Minus 4.
How do you get? Someone said minus 2 or minus 4, which is it? How would I simplify?
Expand the top.
You don't expand the top. The top is already expanded. What would we do here?
I mean, difference of squares.
Difference of squares, so what do you do?
X plus 2. Let's expand this 2.
Right, that's called factoring, not expanding. So we have x plus 2 on the bottom. Now what? Cancel. So I pretty much have x minus 2, and I'm approaching minus 2, so I get negative 4 would be the answer. Now if I did the limit as x approaches minus 2 from the right of this function, I can do this exactly the same thing. I would also get minus 4. So the limit actually exists, and it's equal to minus 4. What is f of minus 4? Of minus 2 is where we're headed. It's undefined, right? Because if I plug in minus 2, I divide by 0. So it means the answer is no, it's not continuous here, because the function is undefined. So my limit actually exists, it gives me a value of minus 4, but the value of the function is not there. What about this one? Well, the top is the same function, so I know that the limit as x approaches minus 2 from the left of this function is going to give me the same as the limit as x approaches minus 2 from the right of that function. They will both give me the answer negative 4, so the limit exists. Now if I ask you, what is f at negative 2? What is that value?
Well, negative 4.
It's negative 4, right? So I said if x is not minus 2, it's this guy. If x is minus 2, it's that guy. It's a piecewise function. So this is actually minus 4. So it is continuous. Right? Now remember, we actually drew this guy before. And remember, it was just a straight line going through minus 2, going up like that. There was a hole here, and it continued going that way. And that happened at minus 2, right? And we knew that this hole was located at minus 4. So basically what this guy did, right? So when I'm not at minus 2, it's this graph. But then I said, okay, at minus 2, I'm going to give the function this value. So basically what I just did is I shaded that in, right? So now it's continuous, right? Because the bad point, minus 2, I redefined the function there. Okay? So now it's actually continuous. What about this one? It's exactly the same function. So I know if I take the limit as I approach minus 2 from the left of my function, I get the same thing as limit approaches minus 2 from the right of that function. That's minus 4. Now what if I ask you the value of the function at minus 2?
0.
It's 0. So what actually happened here? Well, again we had that same picture. There was a gap which happened at minus 2. But what did I do at minus 2? I filled in what y value? I filled in the y value 0. So I actually filled it in up here. I put a point right here. Now the question is, can I draw through minus 2 without lifting my pencil off the page? The answer is no. I'd have to go here, I'd have to stop, fill in the point here, and then come back and start again, right? So now the answer is no, it's not continuous, right? That's what the picture looks like, but I really didn't have to know what the picture looks like. All I did was check the limit. I got minus 4. Look at the value of the function. It's 0. Those two are not the same, right? So it means that I can't actually do that. And you have to remember how to take limits. Remember, there's a sequence of steps that we always do. So you're faced with a random limit. The first thing you try to do is plug in, right? This one you could plug in, so everything is fine. This one you try to plug in. That's always the first step. I couldn't plug in because I divide by 0. So the second step, if you can't plug in, is to try to simplify, right? Use your algebra rules. You might have to factor or rationalize or do something, right? So, and then you try to simplify to the point where you can plug in a number, and if you can, great, you plug it in, and that's actually going to be your answer. right? If you couldn't get an answer from that, it means it either doesn't exist or it's going to go to plus or minus infinity, and you really have to just check the points. Maybe draw the graph, plug in numbers close to that point, or something simple. Anyway, so once you find the limit, which at this point you should know how to find, then you just find the value of the function, and they have to match up. If everything matches up, everything is great. If any one of these guys mess up, then it's not continuous. Continuity is important. Turns out we can only do calculus where we are continuous. And this is a calculus class. We want to do calculus. So by doing calculus, I mean taking derivatives and integrals. So if I want to be able to take a derivative somewhere, I need to be continuous there. So I need to know if my function is going to give me trouble before I actually try to go through the hassle. By the way, I'll illustrate this with an example once we get through derivatives. It does not work. The other way. i.e., we can be continuous but calculus still breaks down. So if I can do calculus, it means the function is continuous, but just because the function is continuous doesn't mean I can do calculus there. So it's possible to be continuous and I still can do calculus. But definitely, if it's not continuous, I definitely can't do calculus. So that's kind of important. Let's talk some more about limits. Limits by comparing functions. So we learned what a limit is and how to compute it. Now I'm going to tell you some shortcuts that you can use in computing certain limits. And one of these shortcuts is by just comparing the functions that are there. So this usually only works with infinite limits or limits at infinity. And here's what we need to know. A useful concept. It's basically knowing how each function behaves with respect to another kind of function as x gets large. So let's say you have log to the base a of x. And comparing that to x to the a, comparing that to a to the x, comparing that to like x factorial, or x to the x. Now it turns out we use this fancy symbol that I'm going to show you here. Basically what this means, how you'd read it, it's like a greater than symbol, right? Or it's like two greater than symbols, one inside the other, right? What it means is that this guy is a lot bigger than that guy, with emphasis on the lot, right? So this is saying that x to the a is way bigger than the log function as x goes to infinity. And in the same way, this is an exponential. This is basically saying that the exponential function is way bigger than this guy as x goes to infinity, right? And so on and so forth, right? So these are telling you who's bigger as you're going to infinity. So in other words, logs are less powerful than polynomials, which are less powerful than exponentials. These two functions we're not really going to see a lot here. You'll see this function in the next class. I'm not really going to talk about it. Don't really think you'll see something like this, but that's just very general verification. These are the three functions that we're going to be using all the time in this class, so you kind of have to know how they relate to each other when x is going to infinity. Polynomials will always beat logs as they're going to infinity. Exponentials will always beat polynomials. And it really doesn't matter which one of these guys we're comparing, right? So if I do something like x to the 1,000th power versus something small like 2 to the x, right? So here the power is 1,000. Here the base is just 2. But it turns out as you're going to infinity, this guy is going to be way bigger than this guy, like way bigger, like a lot. So what happens is in the short term, he might be bigger, right? So for emphasis, we are talking about as x is going to infinity. Now in the short term, the x to the 1,000 might be bigger, right? Because if you're plotting like x to the 1,000, all right, so x to the 1,000 would look like a big parabola. Right, so it's going to be that. So if you're at 0, you're at 0. If you're at 1, the y value is 1, right? Because they just plug in 1 into this. 1 to the 1,000th power is still 1. If you're at 2, it's actually going to be a lot steeper. If you're at 2, you'd have 2 to the 1,000th power, which is going to be a huge number. Right? It's very, very, very big. It's more than there are atoms in the universe. Okay, so now, if I look at this guy, at 0, he's going to give me the value 1, right? At 1, he's going to give me the value 2. At 2, he's going to give me the value 4, right? So in the short run, you see that the polynomial is way bigger. But what I'm saying is by this phrase, what I'm actually telling you is eventually, if you move far enough to the right, the 2 to the x is going to pass the x to the 1,000. So when we start to get x is huge, right? Whatever's happening here doesn't really matter. But there's going to come a point where my x to the 1,000, while it's giving me huge numbers, my 2 to the x is going to pass it, and pass it by a lot. Like a lot. Like really a lot. Like this guy might as well be 0 by that much, right? There's going to come a point where 2 to x is going to be so huge in respect to this, it's like he doesn't matter. Like he might as well not exist. Like, what are you doing? Don't even worry about it, right? So that's what I mean by this sign, right? So if you have an exponential fighting a polynomial, the exponential is going to win. Maybe not today, maybe not tomorrow, but eventually it's going to win. Same thing with a log. If you have a log fighting a polynomial, the polynomial is going to win. Maybe not right now, but eventually it's going to win if you keep going to the right. What does that help us with? How does that help us with limits? let's say I ask you an example. Limit as x goes to infinity of, let's say, x squared divided by 2 to the x. Or I ask you something like limit as x goes to infinity of e to the x over ln x. Or I ask you limit as x goes to infinity to the 7 minus 3x squared plus 1 over x plus what's the 20th plus 2x plus 7. Let's add a 3 to the x up here. So if I ask you a limit like this one, what you're going to start to notice is that your x is going to go to infinity, right? Now remember what we are trying to do here. The first step we're going to try to do with this limit is just plug in the number, right? But plugging in infinity, what's that going to give us? Well, infinity divided by infinity. What is that? Turns out it can be anything. So then you're like, okay, that doesn't actually make any sense. So what you try to do then is maybe simplify. Maybe you can cancel something so that it makes sense to plug in infinity or whatever that means. But how are you going to simplify that? You can't factor, you can't cancel, you can't do anything, right? Plug in larger and larger numbers. Well, how big do you have to go? And would you want to calculate 2 to a huge number? It turns out that that gets big pretty fast. You can plug into your calculator, you're never going to get it, right? So once you start plugging like 2 to the 1,000, your calculator is going to spaz out. It's not going to be able to go that far. But it turns out we can still know what the answer is, right? What happens as x is going to infinity, this guy is huge compared to that guy, right? So what's happening to this fraction is like you now have a fraction where the denominator is tiny, the numerator, the top, is tiny, and the denominator is huge. What kind of number does that give you? Small, but how small? Did you say something? What do you think that's going to tend towards? It's actually going to go towards 0, right? When you start looking at how fractions behave, right, like 1 versus 1 over 10 versus 1 over 1,000 versus 1 over 1,000,000. Notice that what's happening as your numerator is not moving, but your denominator is getting huge, right? This is 1. This guy is 0.1. This guy is 0.001. This guy is 0.000001, right? As the denominator is getting large, you keep getting smaller and smaller and smaller, right? So what you have here is you have a denominator that's large, huge, and the top is small, tiny. 0 is going to be the answer, right? So you don't have to simplify, you don't have to plug in, you don't have to do anything. You just have to know how these two functions relate to each other, right? I have a polynomial versus an exponential. This guy is going to be bigger by a lot, right? So it's like I have a fraction with a huge denominator and small numerator. It's basically going to be 0. If you look at this one, what do you think is going to happen here? Well, this is an exponential versus a logarithm. Exponentials are bigger than polynomials, and polynomials are bigger than logs. So it means that this guy might as well be nothing. So what you have here is a fraction with a huge numerator and a small denominator. What's going to happen to such a fraction? Right, so you imagine the opposite is happening, right? So you have 1 versus 10 over 1 versus 1,000 over 1 versus 1,000,000 over 1. As the top gets bigger and bigger and bigger and the denominator stays small, my number keeps getting bigger and bigger and bigger. The answer here is going to be infinity, right? So this, by the way, we have a phrase for it. This is called a bottom-heavy function. This means as we're going to infinity, the bottom is heavier than the top, right? Now, for all such functions, the limit is going to be 0 as you're going to infinity. This one is top-heavy. For all such functions, you're going to go to infinity if your limit is taken at infinity. Or minus infinity. I put a negative sign here, it would be minus infinity. So let's look at this one. What do you think the answer is going to be here? it's top heavy? Why do you say it's top
Bottom
heavy?
half, because on the numerator, there's an x as an exponential.
So the bottom is just a polynomial, right? Just a normal polynomial. The top has a polynomial there, right? So you have two polynomials fighting each other, but that's not important. The important part is you also have an exponential in the top, right? That guy's an exponential, which means he's going to be bigger, and he's in the numerator, so this is top heavy. It's going to go to infinity. Now, another very important concept that we're going to be using all the time is limits of rational functions. This one's going to be super important. We're actually going to use it to help us grasp. So I think I actually defined this for you before, but let's just remember what a rational function is. A rational function means it has this form, p of x divided by q of x, q not 0, where both p and q are polynomials. So I have two polynomials fighting each other. So right now I'm not comparing two different kinds of functions, I'm comparing two of the same kind of function. I'm comparing one polynomial to another polynomial. And I want to figure out, in this context, what does top heavy mean or bottom heavy, or how things will work out, right? So say I have an x squared versus an x cubed, or an x to the 7th versus an x to the 9th. And how the powers are distributed, how the function is going to behave, I'm going to want to know that. So it turns out the higher power polynomials sort of behave the same way. Like the higher your power, the bigger you are when you're going to infinity by a lot, like a lot. So here are the rules. So let's say I'm taking the limit as x goes to plus or minus infinity of something that looks like this. It turns out for such a function, there are only three possibilities. One, the answer is going to be 0. The answer will be 0 if the degree of q is greater than the degree of p. This is top heavy, bottom heavy. This means the highest power is in the bottom. Right? Degree is just means highest power, right? The degree of a polynomial is the highest power of the polynomial, right? So if the highest power is in the bottom, the answer is going to be 0. You don't have to do anything. Just write equals 0. You don't have to do anything. Now, that's one case where the bottom has the highest power. If the top has the highest power, what's going to happen is it will go to plus or minus infinity. This is if the degree of p is bigger than the degree of q. And at this point, you have to watch the signs to figure out if it's going to the positive or the negative. I'll give you some examples when we do that. So this is if the highest power is in the bottom, you'll always get 0. You don't even have to compute anything. The highest power is on the top, you're going to get plus or minus infinity. Watch the signs, I'm going to show you how to do that. Of course, there's the other case where they're equal, right? What if the highest powers in both the top and bottom are the same? This is what it goes to. It goes to the leading coefficient of p divided by the leading coefficient of q. This is called the ratio of leading coefficients. That will be the answer if the degree of p is equal to the degree of q. You will have one of these three cases all the time. So let's actually do some examples. rule. Make sure you get this, these are the later on, I forgot what chapter, maybe chapter 6, but we're going to be graphing guys that look like this. So, and being able to find the limit is going to be important. I think that's enough for us to get the idea. What's the answer?
Five over 2.
5 over 2 is the answer. How do you know that's the answer?
Because you said that the degree of P has to be equal to the degree of Q, so the relative coefficients and the highest power are 5 and 2.
Right. So I look in the top, who's the highest power? I have x to the 0, x to the 1, x to the 2. That's the highest power. In the bottom, I have x to the 0, x to the 1, x to the 2. That's the highest power. So I figure out who the highest powers are. That's the first step. Second step is to compare the highest powers. They're actually the same. Once the highest powers are the same in the top and bottom, the answer is going to be the ratio of the coefficients, 5 over 2. That's going to be your answer here. What about this one?
Positive infinity?
Well, who's the highest power here?
Yeah. Maybe negative.
X cubed. Who's the highest power on the bottom? X squared. Notice that the cube is bigger than the square. So this is top heavy. The highest power is in the top. So I know it's going to go to infinity. It's either going to be plus or minus. What do? Watch the signs. Notice that I'm plugging in negative infinity, which means I'm plugging in a huge negative number. If I plug in a negative number and I cube it, what do I get? Another negative number, right?
Mm-hmm.
So my top is going to be negative divided by, here, this is square. I plug in a negative number into a square, it's going to turn it positive. So what I'm going to have here is a negative number divided by a positive number, so I know that's going to take a negative sign, and so the answer is going to be the negative infinity. Right? So that's what I mean by watch the signs. You have to figure out, when I'm plugging in positive or negative infinity, what's going to be the sign of each part. And I only do that comparison when I know the top power is higher than the bottom power. What about this one? 0. In the top, the highest power is a cube. In the bottom, the highest power is a fourth. I don't care about the coefficients, don't care about the signs. All I care about is bottom heavy. The highest power is in the bottom. The answer is always going to be 0, whether you're going to plus or minus infinity.
0.
Huh? Coming in? Never mind. Minus 5 over 3. Right? Highest power on the top, x to the 5th. Highest power on the bottom, also x to the 5th. Coefficients is a 5. Coefficient here is a minus 3. So this is going to go to 5 divided by minus 3. Or in other words, negative 5 over 3. Because the highest powers are the same. Right? You identify who's bigger. Doesn't matter what order they come in. It doesn't matter. What about this one? Three. Right? Highest power on the top is a cube. Highest power on the bottom, also a cube. Goes to the coefficients. So that's a 3. There's a 1 here if I don't write it. So it's 3 over 1, which makes that answer 3. What about this one? That answer would be a 1. Highest power on the top is a square. Highest power on the bottom is a square. They're the same, so I go to the coefficients, which is 1 over 1.
I have a question.
Yes.
So when we have those kind of problems where you have, like, for example, 2 degrees, That doesn't mean that the denominator is bigger than the numerator because you have two powers, 2 degrees.
Yeah, you only identify the highest powers. You actually don't care about it.
Oh, because
so
I
you look for the highest powers, and then you're going to see that the highest power is in the bottom.
I thought that having 2 different powers made the denominator bigger than
the power tells you who's bigger. The 4 is bigger than the 3.
Okay, so I ignore the, okay.
Yeah, so, and it doesn't even matter if this number is bigger. Like, it honestly doesn't matter. Like, if I put it here, a 50x to the 4th.
No, I'm not talking about the coefficient. I'm talking about the 2x to the 3rd.
Oh, I don't care. They don't matter.
Okay.
Only the highest powers matter.
Okay.
Because within polynomials, the degrees are actually, they kind of work the same with the same idea. Like x to the n is always way less than x to the n if n is bigger than n, like by far, right? So if I'm x squared versus an x cubed, the x cubed is way bigger. It's like this guy doesn't matter, you might as well do 0. So when I'm looking in the bottom and I have an x to the 4th and an x cubed, I don't care about the x cubed. He's not controlling anything. He's nobody compared to this guy.
Okay.
Right? So you ignore everyone except the highest powers. Those are the ones you're looking for. If the highest power is on the bottom, it's 0. Highest power on the top is going to go to plus or minus infinity. Watch for the signs, how they work out. If the highest power on the top and bottom is the same, it goes to the ratio of their coefficients.
Okay, thank you.
Right? And you don't have to show any work. Usually when we have to do this, it's in the context of a much larger problem. You'll have a lot to do. Otherwise, you don't need to actually do anything here. So I just want you to understand that you're looking at powers and comparing numbers. Any questions on that?
How do you determine the, the negative? For example, I want to go to negative infinity, so it doesn't matter, these do not cancel out, right? Because that's essentially negative infinity.
Whether it's positive or negative is irrelevant when the powers are the same. Because it means both will be negative, so it will cancel out, and the coefficients are what keep them the same. So I just look at the number in front of here and the number in front of here, and I put this.
For example, that one, it has a negative x to a 3rd, so that doesn't determine, it just determines who bigger.
It was a positive. I wrote a positive before. If this was negative, it would be negative this answer. I wrote a positive. I think it just I didn't write it very right. Yeah, because you'd have 3 divided by negative 1.
Mm-hmm.
Another thing we need to know. So with this fact, we end the topic of limits. The following functions are continuous on their domains. Polynomials. In fact, these guys are continuous everywhere at all x values. Exponentials. Right, so an example of a polynomial would be like x squared. The example of an exponential like 2 to the x or e to the x, functions like that. These are continuous on their domain. In fact, an exponential is continuous everywhere. So if I ask you what interval these guys are continuous on, for polynomials it's from negative infinity to positive infinity. I would always be able to graph and never have to lift my pencil, ever. Radicals, as long as I'm on the graph, I'll never have to lift up my pencil, ever. So if it's odd, it's continuous everywhere. For even radicals, it means continuous where inside is not negative. Rational functions are also continuous on their domain. Alright, so this is just continuous where denominator is not 0. Right? But as long as I'm not at a point where the denominator is 0, I don't even have to check continuity, it will automatically be continuous. So those are some functions where as long as you're in the domain of the function, you're continuous, you don't even have to check continuity. Which means it'll be kind of a trick question. So if I ask you on a test, for example, if is y equals 3x cubed plus 7 continuous at x equals 9, you don't have to actually check a limit. Just tell me, yes, it's a polynomial. And that would be your answer. Right? Because polynomials, they're continuous everywhere. So it doesn't matter what x value I tell you, it's going to be continuous there. You actually don't have to check it. Yeah.
What's that? It says continue where?
This denominator not equals 0. Right? So if I were to ask you, is y equals x squared minus 4 over x plus 2 continuous at x equals 10, something other than negative 2, the answer is going to be yes. Right? You don't have to check it. Because this is a rational function, and 10 is in its domain. Right? Because the only number that's not in the domain is minus 2. So as long as I'm in the domain of this kind of function, it's continuous. Right? I actually don't have to check it. We can stop there. So, as I said, Wednesday is the test. Show you guys what to focus on. And after the test, we're actually going to start real calculus. We're actually going to put limits to good use to figuring out what a derivative is. And then the real fun begins. See you guys on Wednesday.